What's going on, Charles? We're going to look here at this parallel circuit. We're going to look at some tricks here and some things we got to understand about parallel circuits that'll help us with both graphs and just general understanding of parallel. And then once they throw a capacitor in here, right? So obviously, hopefully, we know just the basic rules. I'm sure most of y'all at least can look those up or have them memorized. Hopefully you'd have that memorized by now if you've done enough practice, in my opinion. But yeah, so basically the first obvious thing we want to understand is if there's no resistor up here, right? If there's no resistor up here, then it's safe to assume in this circuit that my voltage drop across resistor 1 and my voltage drop across resistor 2 will equal, so let's just go ahead and write that. Voltage drop 1 will equal, negative or just voltage drop, or the total voltage, right, of the source. Same thing here with voltage drop 2. It will also equal that voltage of the source, right? And so the only case that's not happening, whereas if we have some resistor up here, there would be some initial voltage drop, and then whatever was left would also be equal across R1, R2. No matter what the values of R1 and R2 is, the potential difference across that entire branch will equal one another, right? It just matters how much is left. If there's no resistor up here at all, then obviously all of it is across both of them. But if there is resistance up there, then whatever's left of the voltage after that initial drop would also be equal across R1 and R2. Okay, and so one thing, remember, we're kind of assuming this conventional current. And so the other thing we can go ahead and assume is, remember, if they ever give you this I1 here, or sometimes they'll give you I4 or whatever the end is, right? If they, on a parallel circuit, if they give you either of these, that is probably one of the best things they can do, because then you know that the sum across both of these resistors will equal whatever that is, right? And then also for trick, for like getting for quicker on circuit problems and ruling out answers, your current across R1 or R2 individually or together cannot be greater than I1. So a lot of the times they'll say like, oh, I1 is 3 amps. Please give me the following for current of I1 or current of I2. And then like two of the answer choices will be like I1 is 3 and I2 is 0.5, right? And that's not possible, right? Because our I1 and I2 must equal that total, or excuse me, I should write this as IT, and then we'll say this is I1 and this is I2, right? And so here IT is going to be the sum of I1 and I2. So I1, unless there's a short, unless something crazy is going on, I1 cannot equal the total if I2 has any current, and neither one of them can be greater than the total, right? And so that's important. The first important thing to remember there, as well as that voltage drop being equal. And so now we're saying, okay, so we know total current, or we have this variable for total current. And so now let's talk a little bit more about equations and just general understanding of what we could do here. And remember, I'm not solving for any particular answer or any particular question. I'm just showing you guys the relationships and trying to show you how I kind of experiment with these things to get better understanding, right? And so what's going to happen now is if R1 and R2 are equal, that's easy, right? Because the voltage drop across each of them would be the same. And if let's say, let's go ahead and just write that out for you guys. If R1 equals R2, then that's easiest, right? Because that's going to mean that my I1 will equal I2, because the voltage drop, right, V equals IR. And so if R1 and R2 are the same and V is the same, then obviously I has to be the same, right? And so that would be the same, and V1 drop. These are drops, right? So equals V2. Okay, so that would all be the case if they're the same. But what happens when we get a little bit funkier, right? When one is like, let's now say that R2 is equal to 2R1, right? Or, the way this could read on AP exam is the value of R, or the value across the first branch is R, and the value across the second branch is 2R, right? Or something like that. And so now we know, okay, so now there's 2 times the resistance on the second branch as there is on the first branch. What could we do, right? Well, if we have numbers, remember that this the percentage of the resistance that branch has, it'll get the opposite when it comes to the current, right? And so if we had numbers, let's say just for a second that it was 10 and 20, right? Well, then it would be easy to say, okay, well, if this is 10, this is 20, and we're going to say that our I lost my train of thought there for a second. Oh yeah, so for here we could easily say, well, R1 is 10 and the total here is 30, right? So it's getting roughly 33%. I just drew that backwards, but you get the point. 33% of the total resistance, which means it actually gets 66% of the total current. And the opposite would be true for R2, right? R2 is 20 and the total is 30. So it has 2/3 the resistance, which means that it's going to get 1/3 of the current, right? And so that's a really important relationship to understand. That'll help with a lot of problems. But we're going to make it a little bit easier here too, okay? So now we're going to try to come up with something. If I wanted to solve for I1, right? How could I do that? How could I solve for I1 in the form of variables, right? Particularly maybe for response, something like that. So first thing we always want to write, total voltage will equal total current times total resistance, right? And here technically we could go ahead and expand that RT would equal 1 over R1 plus 1 over, let's go ahead and say 2R1, right? And so that technically is true, but I try to stay away from dealing with the whole inverse thing unless you really feel comfortable with it. And then it gets a little easier if we manipulate some variables first, right? So this is that general relationship. And so now what we're going to also say is we also know that I total is equal to I1 plus I2, okay? So we know this also. So now what we're going to do is say, okay, well, if that's true, we also know that my V total across our V1 equals V2, right, as far as the voltage drops go. So then I can also say, okay, well, if V1 equals V2, then that also means that I1 R1 equals I2. And then we're going to keep this as, this would technically be R2, right? But we're going to go ahead and put in R2 R1. Or I1 R1 equals 2 I2 R1. Okay, and so we can already start to see this relationship forming, right? But so then what we can do now is take this equation, if we really wanted to go even further, and say, well, then I1 would be equal to 2I2 R1 over R1, which would be this, which would then say that this means that I1 is equal to 2I2. And so then, okay, well, let's see here. Does this make any sense? Well, if we're saying that R1 is 10 and R2 is 20, so I'm going to say 20. And so then we're saying, well, remember, originally we're saying, okay, 10 over this, so 33%, or means 66% of the current. And then the other one gets 33% of the current. Okay, so now let's just say that my voltage is 12. Well, if my voltage was 12, and we're saying that V over total resistance, let's go ahead and just do a numeric calculation saying 10 and 20 like we used before. So 1 over 10 plus 1 over 20, invert that, would give me 6.67, which is my total resistance. And then we're saying 12 volts, so 12 divided by 6.67 would give me 1.8 amps. And so now we're going to say, well, if that's true, then that means that my one branch should be getting 0.33 times 1.8, which would give me 0.594. And this would give me 1.8 times 0.66, or 1.188. And so now, according to my original formula here, these should be double, right? So it's 1.188 divided by 0.594. What do you know? Exactly 2 times, which proves here that when we solved this gave us that very quick, maybe the first few times it's not super quick, right? But this way we're able to create a relationship here to solve for a particular variable. Even if we don't know the values, we can come up with that conceptual relationship. Okay, so hopefully you could do this for I2, right? And just being able to understand what's going on in these circuits makes it super helpful. So hopefully this helps, and then I'll come out with another video that gets a little bit crazier.